Hi, I'm Colin Walls, and I'm here again to talk about embedded software. Today, I want to revisit a subject I've looked at before, which is quite important, and there are other angles on it, which I want to explore. And that subject is the inlining of C and C++ functions. The concept here is very simple. If you are writing code, particularly if it's being optimized for speed, the compiler could simply take a call to the code, to a function, and insert the actual code of the function. Now that makes sense if you're compiling for speed because you've eliminated the call and return sequence, so the code will execute faster. However, it may make the code overall rather larger simply because if there's multiple calls, each one of them will get a copy of the function. So it only makes sense if you're talking about a small function and if speed is your priority. Now compilers can do that automatically, but there is also the keyword inline. Now that was created in the C++ language and has found its way into C nowadays. It was an extension to many compilers' keyword sets anyway. And what this does is gives a hint to the compiler that inlining might be a cool idea. It's only a hint because if you try to inline a very large function, you generate something rather ridiculous. So that's the idea of inlining. There are one or two issues. One of them is that compilers may generate an out-of-line copy of the function as well. Now why would they do that? Well, there's two reasons. One is some debuggers are just not quite smart enough to deal with inline code. That's not good, but that's the way it is. So you end up with this unnecessary overhead just to deal with debugging. Not a very satisfactory situation. The other reason for having an out-of-line copy is once the function's been declared, it's possible that there will be an extern declaration from another module, and therefore it would need to link to an independent function. So therefore an out-of-line copy is necessary. Now, if you end up with out-of-line copies which are redundant, then a smart linker will sort that out for you. But that's another thing to worry about. A simple way around this is when you create an inline function, make it static. In fact, if you make it static and you compile for speed, you probably don't even need the inline keyword, because the compiler will then know that because the function is local to this particular module, the options in place for this module are the way it should compile the code, and it will inline it appropriately. So that gets you around the problem. Let's look at an example of inlining and we'll talk through the sequence of events. So here we have some code. At the top we have a function called add that simply takes two integer parameters, adds them together and returns the result. Fairly trivial, but here we go, just an example. Underneath this we have a main function, and in there we have two calls to add with different parameters which are returning the result. So that's what the code looks like, and if you compiled it conventionally, then each of the calls to add would indeed produce a call return sequence, and it would do what you want it to do. If we compile with speed as our option, and we allow inlining to occur, then the resulting code will be functionally just like this. So instead of the calls to add, we have the expression z equals x plus y in each place. In that particular case, the code will actually not be any bigger. In fact, it'll probably be smaller overall and faster, so it's a bit of a win-win. Very simple, almost trivial example, but it gives you the idea of what inlining is all about. Just for fun, let me build upon my comment there about it being trivial. As I'm sure several viewers will have figured out already, the triviality of this example will work against me, because what the compiler will actually do with this code is generate something more like this. It will generate z equals 1 plus 2 instead of ever creating the variables x and y. Actually, it'll go one step further than that. The code could end up like this, because the 1 plus 2 gets evaluated at compile time to be 3, and the 3 plus 4 gets evaluated as 7, all at compile time, and the assignments just occur. Actually, it gets even worse, because the compiler will spot that the variable z is never actually used for anything. So we might as well not compile any code at all. So my example comes down to this. I told you it was a trivial example. That's the danger of triviality sometimes. But nevertheless, I hope you get the idea of what inlining is all about. So that's it for today. I will be back soon with another story about embedded software. See you then.